Next, in Chapter 18, we'll look at how do substituents on a benzene ring affect electrophilic aromatic substitution. First, electron-donating groups make an aromatic ring more electron-rich, while electron-withdrawing groups make an aromatic ring less electron-rich. They're pulling electrons away from the ring. So the question that we need to ask is, what is needed in an aromatic ring for it to be able to undergo electrophilic aromatic substitution reactions? The answer is that what is needed is electron density in the aromatic ring, since the aromatic ring is going to be the nucleophile in all of these reactions, reacting with an electrophile. So therefore, electron-donating groups, things that push electrons towards the ring, make the ring more reactive because there's more electron density in the ring to react with an electrophile. While electron-withdrawing groups, things that pull electrons away from the ring, will make the ring less reactive as there's less electron density available. So then the next question that we want to ask is, which groups are electron donating and which ones are electron withdrawing? And to determine this, we must consider two things: inductive effects and resonance effects. So we've looked at some inductive effects already. Inductive effects are based on electronegativity. So atoms that are more electronegative than carbon pull electron density away from carbon. Examples are things like N, O, X. X being generic for halogens. So what does this look like? In aniline, or aminobenzene, you'd note that the nitrogen out here has a delta minus. The carbon here that it's bonded to would have a delta plus because nitrogen is more electronegative than carbon. Or you can draw that as a vector, where the electron density is being pulled towards the nitrogen away from carbon. So this is an inductive effect. The amino group, or the nitrogen, is pulling electron density away from the ring. So this would be an electron withdrawing inductive effect. We may not have talked about it yet, but carbon is very slightly electron donating. So if we have a carbon bonded here, then the inductive effects will be slightly electron donating towards the ring. So it would be electron donating inductive effect. So those are the cases for the inductive effects. Before we can finish each one of these, we have to consider if there are any resonance effects as well. And because we have to balance the resonance effects and the inductive effects to determine the overall picture for whether a group attached to benzene is going to overall be electron donating or electron withdrawing. So now let's look at resonance effects. Now, if you look at resonance effects for aminobenzene or for aniline, you notice the nitrogen has a lone pair of electrons. So the nitrogen can donate that lone pair of electrons. If it does that, this carbon here on the ring would have 5 bonds, so this pair of electrons needs to move out. And when it does so, now you'll notice that there's a negative charge on the ring. The amino group is going to be electron donating through resonance effects. It's electron withdrawing through inductive effects, but it's electron donating through resonance effects. And there are actually 2 more resonance structures that you can draw of this, which will be useful for us to consider for future cases. If we push this negative charge over, we can push this double bond over and move the charge opposite where the nitrogen is. Then we can keep going around the ring and move it again until it's ortho to the nitrogen group. And in this last case, if we push the electron pair back and push this back out on a nitrogen, we end up going all the way back to the start to get our original resonance structure that we drew. So there are 4 different resonance structures you can draw for aniline, 3 of which have negative charges on the ring. The amino group has very strong resonance effects where it puts a partial negative charge on the ring in 3 different locations. This is true anytime that there's an atom that has lone pairs of electrons that are adjacent to the ring. The most common examples are N, O, and X. So let's look at an example that has electron withdrawing resonance. So if I have a carbonyl next to a ring, there's a resonance structure I can draw of a carbonyl. That puts a positive charge next to the ring. So now if I have a positive charge next to the ring, one way that I can get rid of that positive charge is to move electrons from the ring out to get rid of the positive charge. And now that's placed a positive charge in my ring. I can stabilize that by moving the electrons around the ring from where the pi bonds are. And you'll notice, as we keep drawing these resonance structures, that the positive charges will end up ortho to our substituent and para to our substituent. So now that we've seen some electron donating and electron withdrawing resonance and electron donating and electron withdrawing inductive effects, let's put it all together and see what happens when they're combined. So the first question is, what is NH2? Is it going to be donating or withdrawing overall? If you remember, inductive effects from NH2 are withdrawing, and resonance effects are donating. And the answer is that for O or N, resonance effects dominate. Okay, so if resonance effects dominate for NH2, then you can see that it's going to be donating. However, for halogens, inductive effects dominate, and they're going to be overall withdrawing. And for groups with pi bonds next to the ring to heteroatoms, so things besides just carbon-carbon bonds, so that means that any CO double bonds, so things like aldehydes, ketones, acids, anhydrides, amides, CN triple bonds, nitriles, and nitros, nitro groups, NO2, those all are going to be withdrawing due to resonance. So then as we start to analyze whether or not things are electron withdrawing or donating, that can also help us start to have the discussion of whether or not they make the ring more reactive or less reactive. Remember, to do electrophilic aromatic substitution, we need electron density in the ring. So things that are donating, things like NH2, and anything that's going to be donating, that's going to make the ring more reactive. While any things that are withdrawing are going to make the ring less reactive.